I'm running a little late here, but it's Monday, right? Hope you all had a good weekend. No quiz today. And it's not because I didn't want to give a quiz. I actually wanted to give a quiz, but the problem I wanted to give would probably take 20 minutes. And I just didn't, yeah, if you know what you're doing. So I just didn't want to eat up that much class time. So we're just going to move on. We're going to start something new today. We're going to start talking about definite integrals. All right, so if you look at our calendar says that today we're supposed to cover 5.2, 5.3, 5.4. And then the homework says to be announced. So what I'm doing really is I'm taking a bunch of different concepts from 3 sections and I'm just going to deliver it all as one topic, all right? Instead of going through each section. I'm just going to pick the things that I want to talk about. But I will give you a homework assignment at the end of class that comes from the book, all right? So a lot of today is going to be building up to a final result. So a lot of the details of the beginning of this class are just for you to understand what we're doing. It's not necessarily that I'm going to test you on it, but you have to understand what a definite integral is, and then we're going to get to the fundamental theorem of calculus, which is going to be the main result. All right? So where are we going to begin? We're going to start with the idea of trying to find the area of a circle. Okay? So let's imagine that we are thousands of years ago, maybe, trying to find the area of a circle. So how would we have done this thousands of years ago? Hundreds of years ago. Okay, so we don't have a formula, in other words. Nobody has figured out the area is pi r squared, right? So there's a lot of different ways. One way you could do it, and the way that the Chinese did it, is something called the method of exhaustion. Yeah. Nope. That's truly called the method of exhaustion. Did I spell that right? I'm missing an H in there. Whatever, who cares? Not an English class. All right, so the method of exhaustion goes like this. The Chinese said, all right, what we can do, they said, we can measure the area of rectangles and squares without any issues. So they would draw, on a piece of paper, they would draw a very accurate circle. You know, they would get maybe something in the middle with a string, and they would draw a really accurate circle. And then they would go, let me go get my yardstick over here. They would get a very, very precise ruler, and they would start filling this thing with rectangles and squares. So they would, very accurately measure and draw a square in here, all right? So they draw a square. Obviously, the area of that square is less than the area of the circle. So then they'd say, okay, we'll fill this in with a rectangle right there. That gives us a little more area. And then we'll fill that in. And they'd go try and fill in all these little gaps with as many little rectangles and squares as they possibly could. And they would measure each one, and they would add them all up, all right? So imagine if I did that. If I added up all the areas of these blue rectangles and squares, then I'm going to be missing pieces, right? Like this little corner I didn't get, that little corner I didn't get, right? So I would have some error here, right? So the area, add up all these, let's call that the area of the blue, okay? The area of the blue, do you agree, has to be less than or equal to the true area? Yes? Now I put the equals because we know it's less, but it doesn't change anything to put the equals underneath there, right? So then what they would do is they would say, all right, we've got a good idea of a lower bound to this area. This area has to be bigger than that, right? So then they'd start over, they'd have the same circle, and this time they would draw a square around it, like this. Now that square, the area is too much, right? So they'd find the area of that square, And then they'd start subtracting from it all these little rectangles and squares right here. So it's like the big purple one, take away the small purple ones, and that area would be what? Bigger or smaller than the true area? Bigger, right? So they would have the purple one, right? I don't know if you can even tell that that's purple and blue. I know on camera it looks the same, but get the idea? So what they would have is they would be able to squeeze the true area between two numbers that they knew. All right? Make sense? But this was obviously very exhausting to do this, right? Measuring all that stuff. But they got a pretty good approximation for a formula. They pretty much understood, you know, we know the true area is pi r squared, right? They pretty much had gotten it down to 22 over 7 r squared. So they pretty much knew that that number in front, now this is an approximation here. If you do 22 divided by 7 on your calculator, it's approximately pi. It's not pi, but it's close. And so they were able to, with using this method of exhaustion, get pretty close, and for a long time that was an acceptable number to use for areas. Okay? So what we are going to take from this is the idea of trying to add up a bunch of things, right? That's what we are about to try. This was the first motivating problem that kind of led the way for us. Now, think about the real world, right? Why would we want to measure areas? Thinking back again in history, why was there a need to measure areas of things that were not rectangles and squares? Building. Okay, so let's say you have some land, right? You have borders, right? And so, you know, this is mine, this is yours, and stay off my property, right? So you'd want to figure out where your borders are, and sometimes those borders aren't straight. Sometimes a river is going to dictate a border, right? So you want to accurately measure things that are not straight. And circles are not straight. And so if we can measure the area of a circle, that might help us measure the area of something that's really kind of wavy, right? And so that's what we're going to try and do now. We're going to take a function, okay? Our goal right now is to take a function, arbitrary function like this, f, and then just pick some point, let's say A and B, and just imagine just that region right here, right there, this right here. If we wanted to know the area of that, call it A, how would we find it? Okay, and we don't have any formulas for areas other than rectangles and squares. That's it, all right? So would you all agree that if I can do this, if I can find the area of this, then I'm pretty much going to open up my ability to find the area of almost anything, yes? No matter how crazy it is, as long as I can come up with a function that kind of models that curve, then I should be okay, all right? In fact, if you take the equation x squared plus y squared equals r squared, this is a circle of radius r, isn't it? Yes? And if you solve it for y, which I'm not going to go through the details, but if you solve it for y, you get that, right? And if you look at just the positive answer to this, what you get is the top half of the circle, like that. All right? So this, as a function, f of x, just the top half, is the square root of r squared minus x squared, right? So do you agree that if I can find it, or if we can find an arbitrary way of finding the area under any function, then I should be able to find the area underneath this little half circle, this semicircle, right? And thus, I would actually have a formula for the area of a circle. Because I could get like almost a formula for the area of half of a circle, and I just double the answer to get the area of a circle, right? So this would be almost just like one application, one general situation of this more general thing. Or, sorry, more, it's Monday, I'm really tired, I'm sorry. I had a long weekend. So this is the generalization. This would be a specific example where the function is the semicircle, okay? So the way we initially tried to attack this was kind of like the method of exhaustion. So I think the best thing for us to do to understand this is to look at a specific example. We're going to pick a function, pick a really nice one, and then we're going to go about trying to find the area underneath it, all right? But before I can do it, I have to make sure you understand a few things. Okay, so we have some preliminary things to discuss before we move into this. So some prelim stuff. All right, so how many of you are familiar with this? That notation right there. What do we call this? No?
Or limit?
No. This is called sigma notation. Now, you should have covered this in college algebra, but it may have happened that you didn't. All sigma notation is a condensed way of writing addition. So what this stands for is, well, this right here, this symbol is the capital Greek letter S, okay? So this is saying, okay, S, capital S, sum, all right? We're gonna take the sum, and what we're gonna add up are these things, A subscript K. Down here is what we call the starting point or the starting index, and right here is the ending index. So what we're gonna do is we are going to start by letting K be 1. All right, K is gonna start at 1, and it's gonna stop where? At N, and each time I'm gonna add another term, I'm gonna let K go up by 1. So this would be equal to, first I let K be 1, so this would be A subscript 1. Then plus, what's the next one? A subscript 2. Plus A subscript 3, plus, and I keep doing this all the way till I get out to A subscript N, and that's when I stop. All right? So instead of writing out all this stuff, maybe there's like 10,000 of these that you want to add up. Instead of writing all 10,000 of these out, you can condense it down into a nice little notation like this. Right? So this is just notation we use for addition. Now let me give you a specific example. A specific example would be something like this. Sum, let's say K equals 1 to, let's say, 10. Now let's just say K, all right? So what I'm going to do is I'm going to start with K being 1, right? And then I'm going to plug K into this expression, which is just K, right? So this becomes 1 plus what? 2 plus 3, and where do I stop? 10, right? So that's the notation for adding up the first 10 numbers, right? And what is that? Is it 55? Okay. Let's try another one, another example. What would this mean? Sum, let's see, K equals 1 to, let's go to 4. Let's do K squared, just to make sure you understand the notation here. So what would I put first? 1 squared plus 2 squared plus 3 squared plus 4 squared. Okay, and I'd stop at 4. So what's that going to be? 1 plus 4 plus 9 plus 16?
30.
30? Okay, right? All we're trying to make sure is that you understand the notation. Maybe one more? Sum K equals 1 to 100 of 5. So I'm going to start with K being 1, right? But there is no K here. So what's my first term? 5, okay. Then I go plus, now I let K be 2. But it has no effect on it, does it? So what am I going to write down? Well, 5 again, right? 5 again? It would be 10 if there was a K next to this, right? 5K, then it would be 5 times 1, 5 times 2, right? But it's just 5. So I'm going to go, now K is 3, right? Which has no impact on this, but I need to write it down again. So 5 again. I'm going to do this how many times? 100 times. So I have 100 5s added together, which is the same as what? 500, right? It's basically this number times that number. All right? Any questions on that? We'll get to work with this more, trust me. All right? Here are some properties, all right? Some properties of sums that we'll need. You know what? Let's get rid of this. Now, there are a lot of properties when it comes to sums, but these are the ones that I want you to know right now. Properties. Okay, the first one is that if you take the sum k equals 1 to n of a constant c, so that c is a constant, that's just like the problem we just did, right? I did sum k equals 1 to 100 and I did 5 for my constant. And what did we say the answer to this was? C times n. It's this number times that number. Okay, is c times n. All right, next property I want you to, we'll call that property 1. Property 2, if you have sum k equals 1 to n of c times some expression here. So this right here, a sub k means that as k changes, this is going to change. But the c in front's going to stay the same each time. Then this property says, anyone have a guess as to what this property is going to say we can do with that c? Pull it out. This is c times the sum k equals 1 to n of a sub k. So this one is just saying that the constant can come out. Just think about it. Each one of the terms, right? When you start letting k be 1 and 2 and 3, each one of the terms is going to have a c in it, isn't it? So we're just saying that, look, you can pull that c out and then distribute it through to all those later.
So okay, got it.
Sure? Okay. Third and last property we're going to need here today is this one. Sum k equals 1 to n of a sub k plus or minus b sub k is equal to sum k equals 1 to n a sub k plus or minus sum k equals 1 to n of b sub k. Does that seem obvious that that would be the case? It's saying that if you have a sum and inside you've got two things, right, that are being added or subtracted, that you should be able to add them up separately and add those answers together. Now, if you don't believe that this is true or you want to see it a different way, one way you could convince yourself of it is to think about what each one of these is. So, like, look at this one right here. Let's just look at the plus, not the minus for now. If k is 1, what's this first term for the left side? If k is 1. If k is 1, what do we get? A sub 1 plus b sub 1, right? Then we go plus, and now we let k be 2. And what would we have? A sub 2 plus b sub 2. And then plus, now we let k be 3, right? A sub 3 plus b sub 3. And we're going to keep doing this all the way till we get down to the very last one, a sub n plus b sub n, right? That's what the left side of that is saying we do, right? Now, what does the right side say? So this is a question mark. Are these equal? Well, this first one is a1 plus a2 plus a3 plus all the way stop at a sub n. Right, that's this one. And then plus, I'm going to run out of room, b sub 1 plus b sub 2 plus stop at b sub n. Now, are these the same? Yeah, just drop the parentheses, rearrange, and it's all the same, right? So this property seems logical, doesn't it? Do y'all agree or not? Okay. Now, it turns out later, okay, later in this class, chapter 8, that if this sum goes to infinity, which it will, okay, then this property may not hold. Okay, so later on we'll see that this only works sometimes, all right? So for us, because it's finite, because this starts somewhere and stops somewhere, this sum is finite, we can trust that that holds, all right? I don't want to get too deep into these things right now because we just need a few things to get us through today. Then we'll revisit this in chapter 8. Okay, so I've shown you just basically some notation, right? I've shown you 3 properties, and now I'm going to show you 3 special sums. And then we'll be ready to start. 3 special sums. All right, the first one, sum k equals 1 to n of k. All right, now we just looked at that one a second ago. I gave you a specific example. I did sum k equals, I think I did 1 to 10, right? Of k? Didn't I do that? Okay, so I've done this, but now I'm saying let's look at it in general. Like if you start at 1, plug it in, and stop at n, this is just 1 plus 2 plus 3 plus 4, and go all the way out and stop at n, yes? Okay, this is a very special sum. And we actually know what it adds up to be. We have a formula for what it adds up to be. Did I tell you about the kid Gauss in here? No, I haven't done that yet. Maybe I will. This adds up to be n times n plus 1 over 2. So this is a special sum, and the reason it's special is because we actually know what this adds up to be without actually having to do any work. So go back to this example right here. Okay? According to this formula that I just gave you right there, well, what's n for us here? 10. N is 10, right? So according to the formula, if you want to add up 1 plus 2 plus 3 plus 4 all the way out to 10, right? We don't actually have to sit there and calculate it on a calculator. What we can do is just use that formula. So you said n is 10, right? So if I plug in 10 here and 10 here, that should spit out the answer. 10 times 10 plus 1 over 2, that's 10 times 11 over 2, that's 110 over 2, which is 55. And you can verify that on your calculator if you want, that it works. All right? So maybe I should tell you the story right now. I can make it pretty quick, I think. Y'all know we've done elimination in this class, right? When you have a system of equations, we either have substitution or elimination. Elimination actually is named after, it's actually called Gaussian elimination. It's named after a mathematician named Gauss. And there's a story about Gauss that goes back, and it's kind of like folklore. Like we don't know if it's actually really true. But if you look at what Gauss has done, like what he did in mathematics, you kind of believe it, all right? Because he was brilliant. So the story goes, and I have to be quick here, so I'm going to kind of annotate it a little bit. In like first grade, he was in class, and the teacher that day went into the first graders and said, today, he said, what's 1 plus 2 plus 3? And the kids were like, 6, and everyone got it right. And then the teacher said, all right, what's 1 plus 2 plus 3? I want you to do that all the way out to 100. And so the idea was that the teacher just wanted to give them busy work, right? I guess the teacher wanted to sit there and Twitter and all that. No, this is like the 1800s. This is like the 1800s.
Stone and chisel.
Yeah, exactly. Send smoke signals. So this is like the 1800s. So the teacher just wanted to give them some busy work. So the story goes that within a few minutes, Gauss turned over his little chalkboard slate, because that's what they used to write on little chalkboard slates in class, and he turned over and sat there very quietly, because they also had discipline and all those sorts of things back then too. So the teacher kind of looks up, sees Gauss is done, and walks over there, and Gauss has this formula written down. And the teacher's like, okay, well, the formula was known, okay? So Gauss he wasn't like the first person to ever come up with a formula, but he's in first grade, and he's using the formula. The teacher's like, who showed you the formula? And Gauss said, no one showed me the formula. And the teacher didn't believe him. Okay, so Gauss had to explain to his teacher how he figured out the formula. So I'm going to show you how he did it and see if you can follow it. All right? So here was Gauss's explanation. All right, remember, this is only the first special sum, and I'm showing you where it comes from. Okay, so Gauss said this. Gauss said, okay, you want me to add these up. I'm just going to let's call it G just for Gauss, okay? I doubt he did that, but he called it something. He probably called it S for sum. Okay, he said, you want me to add up the first 100 numbers, right? So he wrote it out like that. And he said, well, addition commutes. In other words, it doesn't matter what order you add things when you add things up, right? So Gauss said G is also that list backwards. Okay, so what would be the last number I have here? 1, the one before it, the one before that. Okay? Y'all agree? And then this was like, well, that already was kind of brilliant, but you have to see what he did now. Now he said, look, if these, what I can do is I can add these two together. So like if I add the left sides together, I get 2G's, right? 2G. And if I add straight down, add them like this. And add straight down, what do you get? These first two add to be what? Okay, what's the next one? What's the next one? Okay, not a coincidence, right? They're all going to be 101 the whole way down, all the way till you get to the end. Yes? And then Gauss said, all right, these are all 101s, and I'm going to have how many of them? So I have 1 of them, 2 of them, 3 of them. I'm going to have 100 of them, right? So he said 2G is equal to 100 101s. And he said, but that's twice what I want, so I'm going to just divide both sides by 2. So if I divide by 2, right, I get that. So he said, you know, I have to add to 100. I noticed that it's going to be 100. How did he know this is always going to be one more? Because when you do this, right, these numbers are always going to be one more than that number you stopped at. So if I stopped at 200, this would add down to be 201, 201, 201, 201. I would have 200 of them, right? Make sense? Now, I'm lying to you a little bit, because that's actually not how Gauss did it, because he was even more brilliant than that. It's just that helps students understand what we're doing. So Gauss said, you want me to add up to 100, right? So Gauss said, I'm going to do better. I'm going to go to n. All right? Then he said the number before n is that number take away 1. And the number before that is that number take away 1, so it's that number take away 2, right? So if that's 100, 99, 98, yes? He said, I'm going to write the list backwards. Call it G. That last number is n. The number after that's n minus 1, n minus 2. And then the last one is 1. The one before that's 2. The one before that's 3. And then he added down again. All right? So when you add down, you get 2G. What's the first thing you get when you add together? N plus 1. Okay, what's the next one going to be? N minus 1 plus 2. N plus 1. N minus 2 plus 3. N plus 1. All the way down to the very end. And the last one will also be n plus 1. How many of them are there? Nope, not 100. There's n of them. 1, 2, 3, 4, because you stopped at n this time, right? So he has n plus 1s. So he said 2G is equal to n times n plus 1. And then he said that's twice what I wanted, right? So divide by 2. And now you have a formula.
What were you doing in first grade?
Yeah, what were you doing? I was trying not to pee in my pants.
That's right.
No, so
Inside the lines.
I always think this is a good example of genius because, I mean, look, show of hands, how many of you follow this? Okay? That's not what makes it brilliant. What makes it brilliant is that someone came up with this, right? He saw it. And not only did he see it, he saw it at a very young age. He was able to develop that. That's a very, very unique type of problem solving, right, for that age. And so it makes sense that he went on to do brilliant things, right? Okay. There's another way I can show it to you that's a little more geometric. Look, I'll do it real quick. I'm going to do it with boxes. Okay, so that would be, if I said how many boxes do I have here? This would be 1 box plus 2 plus 3 plus 4 plus 5, right? So this would be like 1 plus 2 plus 3 plus 4 plus 5. Yeah? Okay, so imagine now drawing that same picture upside down. So I'm going to put the first box here. The next 2 are here. The next 3 go there. The next 4 go there. And then the 5 go there. Yes? Okay, so how many boxes do we have total here? The total. This would be how many of them? 5 of them. And then this side is how many? It's the 5 plus the 1, so that's 6. So I have 30 total. If I divide that by 2, that's how many I would have had to start. Does that make sense? If I want to know what this is, I could do 5 times 6 and then divide by 2. So if you do this more generally, let's say that you do these boxes, you know, but you go up and you make the final height n, right? And then flip them over, then this side will always be n plus 1 and this side will always be n, and then you multiply and divide by 2. I'm not going to get any more into it, but you can do it geometrically. Okay. So that is a formula we will need. The next special formula is the sum of not k, but k squared. So this means 1 squared plus 2 squared plus 3 squared plus 4 squared, right? And you stop all the way at n squared. And the formula for this one, I'm not going to prove, you're just going to have to take this one on faith, is n times n plus 1 times 2n plus 1 all over 6. All right, so I showed you this one Gauss's way, and I tried to show you with some boxes, so hopefully you're convinced that that's true. Here, you're just going to have to believe me. Yes? Is that all right with you? Okay. Now, this next one, the last one, is the sum of the cubes. So 1 cubed plus 2 cubed plus 3 cubed, all the way out till you get to n cubed. And that formula is n times n plus 1 over 2. Wait a minute, it can't be the same as that one, right? That can't be the same, right? It's not. It's this thing squared, okay? So these two are almost identical. The only difference is that this one is squared. Again, don't ask why, don't ask me to prove. If you want me to prove it, I'll prove it in my office. I can prove these to you. But I'm not going to do it here, all right? And we could keep going, actually. There's formulas for k to the 4th, to the 5th, to the 6th. There's formulas for a bunch of them. There's not a general. Not that I know of where you can, like k, yeah, we'd probably not use x, but yeah, let's say like k to the m, right? Then the formula becomes blah with m in it. I don't think I've ever seen something like that. Mm-mm.
I have a question.
Yes.
Is any of this in the formula sheets or anything you're aware of?
I do not believe they're not, well, no, I don't think they are. I don't think they are. But you know what? I mean, you're not going to be tested on these.
Oh, okay.
Okay? We're just building up to something. Remember, the whole idea today, what I'm going to do is I'm going to make you suffer for a little while. You're going to see how bad the method of exhaustion is, and then we will have a major appreciation for the fundamental theorem of calculus. Okay? All right, so let's put ourselves back in time again. We're trying to find the area under a function, right? Trying to figure out a way to find the area under a function. We know a little bit about sums, the notation, and there's a few things we know the sums of, like we don't actually have to add these up, as long as they look like k squared, k cubed. Okay, that's where we are. So now let's take a look at a function, a specific example, and let's see if we can try and figure out the area underneath the function. All right, so here it is, specific example. We are going to try and find the area under the function f of x. We're going to start off real simple, equals x squared on the interval 1, 5. So geometrically speaking, we have a function, starts here at 1, ends at 5. It looks like a parabola, right? Goes up like that. And what we're doing is we're imagining dropping straight down from the two endpoints and trying to find that area right there. right? Yes?
Is this the one where you can use, like, you can create a triangle and a square and then do like 1/2 pH and then have the square?
You can do a rectangle. I don't know about triangle.
Yeah. Well, like, I remember in Power 1 we did something where you could, it's almost like a rhombus.
Trapezoidal?
Trapezoid.
Yeah, this is leading, yes. I'm not going to touch trapezoids though because it's not going to matter at the end. But we'll talk a little bit about it. Okay, so we want to find this area, right? That's our goal. If we can somehow find this area, then we will have made major progress. So we're going to do kind of a method of exhaustion. All right? We're going to take that picture, and I'm going to zoom in on it. I just want to draw a quick picture over there. I'm going to zoom in on that picture. Here's 1. Here's 5. And I realize that that's way up there at 25, but just for the sake of scale, yeah, like there we go. Okay? So we're trying to find the area under that. So there's a couple of numbers in between here, right? We have like 2, 3, 4, right? Okay, so one thing I could do, tell me if you agree with this. I could estimate the area of that thing by just drawing, don't draw this, okay? But I could draw a rectangle that goes along the entire width of the interval. Then what I could do is I could plug 5 into the function that would take me up here to 25 and then go over, and that rectangle would be an approximation, wouldn't it? A very, very bad approximation, wouldn't it? It would be too much. Do y'all agree with that? Like that would not be an acceptable approximation. But it's kind of like, remember when we did the circle and I drew a square around it and said, then we're going to come through and subtract all these little boxes in it? This is like drawing the square and saying, okay, that's my approximation. It's not that good, but I could do that, right? Yes? Okay, so maybe we could do a little better. How could we do a little better than that? Because all we can do is rectangles. Instead of doing one rectangle, how about I do 2 of them? So why don't I do this? Instead of going the whole distance across, why don't I go halfway? Okay? If I go halfway, plug 3 into the function, it's going to take me up to here, right? How tall is that piece? From here to here? 9, because remember the function's x squared, right? So this is 9 high. This is, how wide is this? 2 over and down. Now that wouldn't be that great, right? I still have a lot of error there. But I could do another rectangle that goes here, goes up, and goes over, across, and down. So basically this rectangle would be how wide? 2. How tall? 9. And so the area of that would be 18. Then this would be 2 wide, and how tall? 25. So the area of that would be 50. 50 and 18 would be 68, right? That would be not good, but it would be better than the first way, right? The first way was all the way up, all the way over, all the way down, right? And that would have been 4 wide and 25 high, which would have been 100. So we said the area of that's 100. Now we're at what, 68? How could we even get better? What's that? More rectangles, right? More rectangles. So let's go and try and do, I mean, we're just trying to visually think through this right now. So that would be better than the first one. But what if instead of going every 2, I just go every 1? So I go over, I go up, I plug in. How tall is that one? 4, over and down. So the area of that, I'm going to put it in here this time. What's the area of that one? How wide? 1 now. Tall? 4, so that's 4. Here, up, over, down. That'd be 9 times 1, so that's 9. And then I go over, up, over, down. What's the area of that one? 16. And then last, up, over, down, we get 25. Now we add those up. What do we get? 54? Yeah. 54? Okay. So if I make a list right now, yeah, I'll do it right here. When I had one rectangle, let's do it this way. Rectangle and then approximation. the approximate area. When we did 1, the area was 4 times 25 was 100, right? When we did 2, it was 68, right? Now that we've done 4, we've got it down to, what was it again? 54. 54, okay? So it seems like it's getting closer, and the reason that it's getting closer is because these little corners here, where we have the error, is getting smaller, right? It's getting smaller. So how could we even get better? Go half, right? Instead of going 1 wide, let's go half wide. So what would happen there? Well, you know what? That becomes kind of a pain in the butt, doesn't it? So why don't we do this instead?
We don't know, we only know rectangles, we don't know triangles, right?
Well, yeah, they're a little harder to calculate, but we can always find the area of triangles. Yeah. Make a triangle on top? Yes, I'll address that in a second. That has to do with the trapezoidal thing that was brought up a second ago. Let me see here, where is it? There we go. Come on, man, there it is. Okay, now this might be a little hard to read the numbers, but right now, this is the example we're doing right now, okay? And we just did that a second ago, didn't we? We did go 1 and then up and over, and then 1 wide, up and over, right? And when we added those up, we got 54, didn't we? I know it's hard to see this, but it says 54 there. Maybe if I go a little bigger. Yeah, and now I need to make this smaller. Okay, that a little easier to see? Okay, so when we have 4 rectangles, we have an area of 54. Now, this is the actual area. The true area I've already calculated for us. It's 41.3333 repeated. So it's 41 and a third exactly. But we can do better by doing more rectangles. So let me do more. How about we do, instead of, let's do 6. So look at that. When I do 6, I'm having the computer add up. Look what we're at, 49.6, right? All right, what if we do, I could do 7, but here's 8, right? I can do 9, 10, and just keep an eye on this number. It's getting closer and closer, right? And look at these rectangles, right? That number, 42 point something, it's converging, it's getting closer. Well, oh, I stopped, my code stopped. I stopped it at 70. I thought it was, we don't need to go further than that. But look at that, 70 rectangles. We're pretty close to the true area, right? Yeah, we're pretty close, not bad. Okay. So if we wanted to really get the true area, what would have to happen? For us to get the true area, what would have to happen in terms of these rectangles? They'd what? We'd have to have an infinite number of them. Right? But what's wrong with that idea? Well, we can let things go to infinity, right? That's something that we've learned in Cal 1, right? You can take a limit as something goes to infinity, and we found answers in Cal 1. So the idea of saying that we want the number of rectangles here to go to infinity is a reasonable idea. But what seems wrong with it in terms of what's happening to our rectangles? The widths are going to get, if we go to an infinite number of rectangles, then our widths are going to head to where? They're going to head to 0, aren't they? And so when we try and calculate an area, remember the area that we've been doing these rectangles, it's always been length times width, right? Or height times width. The width is headed to 0, isn't it? And we know that in calculus, you know, if something goes to 0 here, right, and this doesn't go to 0, then we should be headed to 0. So there's kind of like this, the idea is we want an infinite number of rectangles, but we're going to run into an issue. Yes? Okay. So now what we're going to do is we're going to see if we can take what we've done now and formulate a general formula for this problem. Okay, let's see how far I can push here. We're still working with this. We still have the same x squared function. Okay, we're going to still start at 1 and we're still going to start at 5, or end at 5. What we're going to do is we're going to try and figure out if we can come up with a formula right now for the area if we had n rectangles. Not 2 rectangles, not 4 rectangles, but n of them, all right? So I'm going to take this interval and I'm going to cut it into pieces, equal length pieces. So I have all these cuts in here, and then I've got all these rectangles in here, right? Agreed? And there's n rectangles in there. So we have n rectangles. Rectangles. All right, so let's talk about rectangle 1. Let's go back and take a look at this very first one. I go right here to this point, I go up and I go over and I go down, I find that area right there. Right? So let's talk about rectangle 1. Rectangle 1. Can you tell me about how wide it is? How wide is it? N?
Yeah, wouldn't it be in?
So think about it this way. When we had the first one we started with, we had one rectangle. How wide was it? When we had one rectangle, how wide was it?
Oh, I guess it would be.
It was 4 units, right? From 1 to 5. So it was 4 units. When we had 2 rectangles, each one was 2 wide, right? With me?
Yeah.
When we had 4 rectangles, each one was 1 wide. Yes? Guys? Just keep it down, please. Yeah. So, one rectangle we were 4 wide, 2 rectangles we were 2 wide, 4 rectangles we were 1 wide.
So this would apply to one of those some formulas.
It's going to. I'm just trying to see, if I break this up into n pieces, right? How wide is each one?
N plus 1.
What's the distance from here to here? That's 5 minus 1, that's 4, right? We know it's 4 wide, right? It's 4 wide. And we've broken it up into n pieces. So each one should be 4 over n. So if we had 1 rectangle, the width of each one would be 1. If we had 2 rectangles, the width would be 4 over 2, which is 2. If we had 4 rectangles, it would be 4 over 4 would be 1. Yes? 1 wide. So the width of this first rectangle, that width, is 4 over n. That's the width of the interval divided by how many rectangles we have, right? That's how wide it is. Okay, so I'm going to put that here. That's how wide it is. That's the width. How tall is it? How tall is this? This is the harder part. How tall is this rectangle? So what I did is I went to that point, I plugged it into the function, right, to figure out the height. So we have to figure out what is that point. It is something squared, but what is that point? What is the x-coordinate of that point? Is it 1? It's not 5, right? It's 1. It's 1. But how far over did we move? We moved by that much, right? So we started here at 1, and then to get to the right end of that rectangle, we moved over 4 over n. Okay, so would you agree that the height of that rectangle, I need a little more room, is the function evaluated at 1 plus 4 over n? Width of the rectangle is 4 over n. The height of the rectangle is the function evaluated at 1 plus 4 over n. Now this does turn out to be 1 plus 4 over n squared times 4 over n. Now where is this square coming from? The function itself is the squared function, right? Had the function been the cube function, I put cubed here. Yes? Okay, that's the area of rectangle 1. What's the area of rectangle 2? Okay, how wide is rectangle 2? How wide is it?
Not 1.
No.
How wide is it?
How wide is it? How wide was our first rectangle? Nope, that's the right, that was the end point. What's the width of it though? 4 over n still, right? All of our rectangles are going to have the same width, 4 over n. It's the heights that are going to be different. So we still have 4 over n here for our width, but in front of it, it's going to be the function I need a little more room. It's going to be the function evaluated where? Okay, so now I'm here, right, at the second one. So what is that? The way I like to look at it is this. We start at 1, right? And now we're going to go and move over by this much twice, right? So I'm going to put 1 plus 4 over n plus 4 over n again. That should move me over 2 places. So I'm going to write it this way, 2 times 4 over n. Right? And then I could square that and do that, but I'm just going to leave it like this. Okay, what about the next one? Third rectangle. Okay, how wide is the third rectangle? 4 over n. Okay, now I'm going to be doing f evaluated where? 1 plus, now 3 jumps of 4 over n, right? 3 jumps of 4 over n. So that would be, start at 1, 1, 2, 3. And then I keep doing this, right? In fact, if I go to the kth rectangle, not the nth rectangle, if I go to the kth one, what would be the formula for the kth one? The function evaluated at 1 plus how many jumps? K jumps of how much? 4 over n, right? Times what? 4 over n. You with me? So if you look back at this, what is the only thing changing in these formulas from rectangle 1, 2, 3 to the kth rectangle? What's the only thing in the formula changing? The value of k. This thing right here. So this was like one of those, right? One of those, then we have 2 of them, then 3 of them, then k of them, right? So this number right here is the only thing changing in these formulas. Everything else is exactly the same, isn't it? And what are we going to do if we're going to do n rectangles at the end of the day? Don't we want to add them up? Yes? So we want to take rectangle 1 plus rectangle 2 plus rectangle 3 plus rectangle 4, right? So can I somehow write the area, okay? The area should be approximately equal to R1 plus R2 plus R3 plus all the way out to my nth rectangle, yes? The area should be approximately that. The bigger n is, the better the approximation. So now I'm going to write that in sigma notation, right? K equals 1 to n of R sub k. That's just the same thing written in sigma notation, right? And now let's replace R sub k with what it is. This is R sub k, right? Right here. So this is going to be sum k equals 1 to n of f of 1 plus k times 4 over n times 4 over n. Any questions? Isn't this fun? So now let's actually figure out what this is. If we plug this into the function was the x squared function, right? So I can get rid of the f because I know the function we're talking about right now. So this becomes sum k equals 1 to n of what? What am I plugging into the function? 1 plus k times 4 over n. And this function does what to that? What does this function do? Squares it, right? So it takes that and squares it, and then I still have 4 over n on the outside. And this, if I can figure out what this sum is, I will have a formula for the area of n rectangles added up together. For only this function, only the x squared, that's it. This doesn't work in general. It's just for this particular function. So what I'm going to do now is I'm going to actually square this. Okay? I'm going to square it. So it's time to do some algebra. If I square that, I get sum k equals 1 to n of, okay, when I square that, I FOIL it, right, with itself, I should get 1 plus what? You all know what I'm doing here? 1 plus k times 4 over n times itself, 1 plus k times 4 over n. So 1 and then 4. So 2 of those. So I'll do it that way. I'll just write plus 2 times k times 4 over n. That's the middle term. Plus all that squared. Plus, I'm going to do it this way. K squared times 16 over n squared. Does everyone understand that's just this FOILed out? Okay, and then what do we still have tacked on to the end of that? 4 over n, right? 4 over n. It is a constant in the sense that n is the number of rectangles we have, but it can't come out of the sum because the sum is controlled by n also. So it has to stay in, but it's okay, it's going to still work. All right, y'all good with that? Okay, we've got just a few more lines and then we'll be ready to crank this thing out. So now we have sum k equals 1 to n. All right, what I'm going to do now is I'm going to distribute the 4 over n through here, and here, and here. All right, so what happens when I distribute it over that first one? I get 4 over n. Okay, plus, okay, when I distribute here to here, I'm going to get 2 times 4 times 4, right? 32k over n squared. I'll write it like that. Okay, so that's this hitting this. And then when I go from here to here, I get 4 times 16 is 64, 64, 64, k squared over n cubed, right?
You reorder that so that it's quadratic. Unless you don't want to.
Well, what I'm going to do now is I'm going to use the properties of sums that we just talked about. I have the sum of 3 things being added, don't I? So I can do the sum of each one. So I'm going to do it like this. Sum k equals 1 to n of 4 over n plus sum k equals 1 to n of 32k over n squared, and then plus sum k equals 1 to n of 64k squared over n cubed. That's a property, allows me to split it up into 3 sums, right? And I'm going to do one more thing. I think one more thing. Sum k equals 1 to n of 4 over n plus sum k equals 1 to n of 32 over n squared times k, and then plus sum k equals 1 to n of 64 over n cubed times k squared. So all I did there was kind of peeled the k's off, right? I just peeled this k out here, the k squared and that k, right? That's all I did. And now, the question, the statement earlier was, this is a constant, right? 4 over n is a constant. We have to be careful. N is the number of rectangles we have, right? So n is supposed to be like fixed in the problem. Like we're going to say, hey, we want 1,000 rectangles. And then if we had 1,000, we would have a number here, right, and a number here, right? So imagine right now, if n was 1,000, that would be 1,000, that would be 1,000. And then this would be a constant, wouldn't it? Yes? Okay. So what happens if you have the sum from k equals 1 to n of a constant. What is it?